I'm Fu Yucheng from the University of Hong Kong, and this is joint work with Feng Weiming. Today I'll talk about approximate the F divergence between two Ising models. And let's set up the notation quickly. An Ising model is specified by a graph G equals to V and E. A symmetric interaction matrix J on every edges and an external field vector H in every vertex. Given a configuration sigma, where blue represents for negative and red represents for positive, and the wave function W of this sigma equals to the exponential of half sigma transpose times J times sigma plus H transpose sigma. And hence we can define a Gibbs distribution mu corresponding to this Ising model, where mu sigma equals to the weight function W sigma over Z, where Z is the partition function, is equals to the summation over of the weight function over all the configurations. And intuitively, the external field vector HV is greater than 0 implies that this vertex V prefers to be positive, and if the interaction JUV is greater than 0, it implies U and V prefer to be the same. And similarly, if JUV is negative, it implies that U and V prefer to be different, and HV is negative implies V prefers to be negative. So Ising model defines a high-dimensional Gibbs distribution with local interactions. The Ising model comes from the statistical physics, where it is used to explaining the ferromagnetism. And in machine learning, the Ising model is a central example of an energy-based model. For example, the Boltzmann machine, the Sherrington-Kirkpatrick model, and the Markov random field. And the graph shows that the Ising models at different temperatures. When the temperature is low, the interaction matrix is very powerful, so the Ising models prefer to be monotone, and as temperature going high, the Ising model is prefer to be show the external field. So our question is that given two Ising models G mu, J nu H nu, and G J mu H mu, how to compute the difference between two Ising models? Here we have two graphs G J mu H mu and G J nu H nu. Our first question is how to measure the difference of two distributions. Now we introduce the F divergence. So we use the F divergence to give to quantify the difference between two Ising models, where the F divergence is the expectation of X from mu, sample from mu, F of nu over mu. And here are some examples. For total variation distance corresponds to F equals to half times X subtract 1 absolute value. And for chi-square divergence corresponds to F equals to half X minus 1 to the power of 2, and the KL divergence corresponds to F equals to X ln X subtract X plus 1. So here are some commonly used divergences. For example, the chi-alpha divergence, the alpha divergence, the square-Heilinger divergence, and the Jensen-Shannon divergence. We'll study the following problem. With input two Ising models mu and nu, and a convex continuous function f arrow epsilon, and we want to output a random number hat d with high probability such as the hat d is a relative error approximation of the real F divergence. In this talk, we will only focus on chi-alpha divergence for positive integer alpha, and for the other divergences, we will shortly briefly introduce them, and we have a similar algorithm for them. And our second question is that, can we compute the F divergence in polynomial time? The previous works only consider the TV distance, which is the chi-alpha divergence for alpha only equals to 1. And in BGMM PV22, they show that the exactly compute TV distance between two product distributions is sharply hard, where the product distribution can be regarded as a Ising model with on the empty graphs with no interaction matrix. In FLY25, they gave an appearance for TV distance for a certain class of Ising models, which is in the Unix regime, where we will introduce the Unix regime later. And BGMM PV24, they show that there is no appearance for TV distance between Ising models beyond the Unix regime unless NP is in RP. And there are also works approximate the TV distance for other graphical models. And we will reduce the approximate problem to sampling and approximate counting problem on Ising models. We will assume two oracles here. First is sampling oracle. The sampling oracle allows us to draw a random sample x from mu with error epsilon in time t sampling g epsilon, and an approximate counting oracle allows us to approximate the partition function z with error epsilon in time t counting g epsilon. So for two oracles, we can call them, and in some time, the sampling oracle gives us a sample x from mu, and the approximate counting oracle gives us a hat z is a relative error approximation of the real partition function z. Our main theorem is that for a constant positive integer alpha, and two Ising models G, J nu, H nu, and G, J mu, H mu, they satisfy the marginal lower bound condition, which we'll introduce later, and we define a family of Ising models F nu mu alpha equals to a lot of Ising models G, JK, HK, where JK is K times J nu subtracts K minus 1 times J mu, and HK is K times H nu subtract K minus 1 H mu for all K between 0 and alpha. Our main theorem is that if all Ising models in this family admit polynomial time sampling and approximate counting oracle, then we give an F-series for approximating chi-alpha divergence. Now we introduce our marginal lower bound condition. Let a constant b greater than or equal to 0. We will assume that our input Ising model satisfies b marginal lower bound, which is for any subset of vertex lambda and arbitrary penny sigma on this subset lambda, and for any other vertex v is not in the lambda, and with probability at least b, this vertex v is going to be positive, and also with probability at least b, this vertex is going to be negative. This assumption is natural and appear in many other works, and our results only consider the Ising models with such marginal lower bound. And we will apply our abstract theorem on such simplified Ising models first. So let us consider a class of simplified Ising models defined on graph G. And there is no external field, which is HV equals to 0 for all V. And all edges UV has the same interaction JUV equals to ln beta. And we will describe such Ising models as the tuple G and beta. So sampling and counting, for sampling and counting problems, there are some known results for such simplified Ising models. And the uniqueness condition is that when G is a delta regular graph, and we can set the uniqueness threshold beta c equals to half ln beta subtract 2 divided by delta. If beta is greater than or equal to beta c, there exists an appearance for sampling and approximate counting. Otherwise, unless NP is in RP, there is no appearance can sample or approximate counting in such Ising models. So in the graph below, there is a threshold beta c. When the beta is below this threshold, it is hard to sample or approximate count. And when the beta is greater than beta c, there exists an appearance. We remark that our definition for the family of Ising models, and on the simplified Ising models, we can describe the case Ising model in our family is G beta k, where beta k is beta nu to the power of k divided by beta mu to the power of k minus 1. To apply our mini theorem on the simplified Ising models, we have two cases below. The first case is that the beta nu is greater than or equal to beta mu. There exists an appearance if beta mu is greater than the threshold beta c. For example, here is the threshold beta c, and here is beta mu, and here is beta nu, and our beta 2 to beta alpha is all above the uniqueness threshold beta c. And the second case is that the beta nu is less than or equal to beta mu. And our theorem says that the appearance exists if beta alpha is greater than or equal to the threshold beta c, which is beta mu is the largest one and beta nu is smaller, and beta alpha minus 1 is smaller, and beta alpha is the smallest one. If the smallest one, beta alpha, is also greater than the threshold beta c, we have an appearance. And now we give a phase transition theorem. For the simplified Ising model G beta nu and G beta mu, where the nu and mu are all in the uniqueness regime, but the Ising model G beta alpha is below the uniqueness regime, there is no appearance for approximating the chi alpha divergence unless NP is in RP. So we remarked the previous work that the appearance exists if beta alpha is greater than or equal to the threshold beta c, and otherwise if beta alpha is less than beta c, there is no appearance unless NP is in RP. So for our algorithm, we'll also introduce the parameter distance. For two Ising models G, J nu, H nu, and G, J mu, H mu, we define parameter distance as below, which is the maximum of the differences between the edges and the maximum between the difference of vertices. For here, we have two Ising models G, J mu, H mu, and G, J nu, H nu, and we compared them, their difference between the edges and the difference between vertices. With B marginal lower bound, FLY25 shows that the two distance is at least B squared over 2 times the parameter distance. And we extend this theorem by data processing inequality, and we give that the f divergence is at least f of 1 plus or minus b squared over 2 times parameter distance. For two Ising models with marginal lower bound, the chi-alpha divergence is that the chi-alpha divergence is at least polynomial of n times the parameter distance to the power of alpha. And our algorithm can be overviewed as below, given two Ising models G nu h nu and G mu h mu. We can first compute their parameter distance in polynomial time and divide into two cases based on the if parameter distance is large or small. So first we input two Ising models and compute their parameter distance. If the parameter distance is small, then it implies the two Ising models are close up to all parameters. And otherwise, we give a lower bound for the f divergence. And for two cases, we all give a f years separately. When parameter distance is small, the f divergence can be shown as below, which is the acceleration of mu times of f of the weight function w and times the ratio of partition function z. Our algorithm draws samples from mu and computes the ratio of the weight function of the samples. Then we compute the mean of and using the mean to approximate the expectation of w, which is the ratio of the partition functions. Then we return the height z equals to the mean of all f of wi divided by w bar. As parameter distance is small, the ratio has a small variance, and our estimator concentrates around the real f divergence with high probability. When parameter distance is large, we can use the binomial expansion and define the estimators as below. Wk plus equals to z mu to the power of k minus 1 times the zk, where zk is the case the partition function of the case Ising model in the family f, and otherwise it equals to 0. And similarly, we define the wk minus. So we can sample x from the case Ising model and consider the value of the estimators. Our algorithm is for each k we draw samples from the case Ising model G, jk, hk and compute the w plus or minus k of sigma. Then we compute the means of wk plus and minus, and using them to approximate the expectation. And finally, we substitute this into the formula above and return a height d. We cannot accurately compute and compare the value of mu sigma and nu sigma when they are really close, but the error led by this misclassification does not affect our relative approximation. And for other divergences, we need the following condition. When the parameter distance is small, the function f is small, has to have some smoothness condition, and which is verified for all commonly used f divergence below. And when the parameter distance is large, f divergence is lower bounded by our poly n, and the additive error approximate is easy when the function f is not does not have the calculation for the absolute value. And we have open problems as below. The first is that can we remove the marginal lower bound assumption, And second, can we extend this result to general graphical models, for example, the Bayesian networks or general distributions? And third, for non-integer alpha, can we get a tight result for k-alpha divergence, since our algorithm only focus on the positive integer alpha? And finally, can we give a deterministic algorithm? And that is all of our work, and thank you for listening.